So I want to discuss kernels generally for the next few slides. But before I do that, I want to motivate kernels using the Perceptron model. So remember with the Perceptron that we have covariates xi for the ith data point in Rd, so that Rd plus 1, so that plus 1 implies that I've added a dimension to x that's equal to 1 to count for the offset. And with each xi, we have a label yi that's either plus 1 or minus 1. So we are going to do plus 1, minus 1. And we have n of these pairs. So if you recall, for the Perceptron, we constructed a hyperplane, W. We constructed our decision boundary defined by the vector W as a sum of these misclassified observations. So let M be a set that's sequentially constructed of misclassified examples. So remember with the Perceptron, the way that we updated W at iteration t plus 1 is that we set it equal to W at iteration t plus yi xi, where we picked the pair yi xi to be a misclassified example according to our current vector W. So if Wt plus 1 is simply constructed by taking Wt and adding this misclassified example, the same holds for Wt. And so if we unfold what each of these vectors are, we ultimately get to this sort of a representation. So our final classifier, our final decision boundary is defined by a sum of a sequence of misclassified examples times the label that is associated with that example. So this is what we end up with. So now let's think how we would use the result of the Perceptron to predict a new label for a new covariate vector that's coming into us. So we want to predict a y0 for a new x0. And the way that we do this is we simply declare y0 to be the sign of the dot product between x0 and the classifier that we learned W. Well, if we look at what W actually is, this is simply equal to the dot product between x0 and xi for I in some set M. So we do this for each xi in this set, multiply it by its label, sum them up, and then take the sign of that. So up to now, we've taken feature expansions for granted. We said let x just be some function of the original x. Let's now explicitly write this as the feature mapping function phi. So if we want to, instead of working in the original space x in Rd plus 1, if we want to now map this to a much higher dimension, we define the mapping function to be phi. So phi takes in x0, and then it maps it to a higher dimension according to some definition of the feature expansion that we want to use. And then we simply do linear classification in that higher dimensional space. So in the projected space, what we're doing is we map x0 into the higher dimensional space. Then we take the dot product with W that was learned in that higher dimensional space and declare the label to be the sign of that dot product. Now if we again unpack what W actually is, remember we're working in the higher dimensional mapped space, so these xi's suddenly become the function phi of xi. So this is simply xi projected into the same exact space that we project x0 into. And so now our dot product is between the feature expanded vectors for x0 and xi. And so this is simply what we're going to call the kernel between the pair x0 and xi. Okay, so now let's actually define a kernel in the abstract, and then we'll come back to it and look at it in some examples. So a kernel, call it K, it's a function that takes two inputs, both in the space Rd, and maps that to an output in R. So it's a function of two inputs in some space Rd, and it takes those two inputs, does a function of them, and maps that to just a real valued output. So R1. D is arbitrary, but the output is a real valued number. Also, it's a symmetric function, so k of x1, x2 is equal to k of x2, x1. And furthermore, if we take a set of n data points, x1 to xn, all of them in Rd, and we construct an n by n matrix. So these are n arbitrarily chosen points. And we construct an n by n matrix K, where the ijth value in that matrix is just the kernel between xi, the kernel function between xi and xj. Then this n by n matrix is a positive semidefinite matrix. And so intuitively what that means is that K satisfies the properties of a covariance matrix. You don't need to think in those terms, but that's some intuition about how we could think about K as a covariance matrix. So there's an important theorem that we're not going to prove, but we're just going to state, called Mercer's theorem. And that theorem says that if we can come up with some kernel function K that satisfies the properties defined here, then there exists some mapping function phi that takes a vector in the original space Rd, maps it to some other space R capital D, such that the kernel function between xi and xj is the dot product between their respective mappings. And so it's important to know that this is for any pairs of xi, xj that we can come up with. If this is satisfied for every single set of n vectors in Rd, where n is arbitrary and the vectors themselves are arbitrary, then there exists some function phi, which is a function that's one function. It takes in any particular x and it performs the same function on that particular x to map it to another space, and we can then have this dot product representation of the kernel function. So this is not interesting when we actually define the mapping function phi. If we define phi first, and then we define k to be the dot product, so essentially we start from this definition. We start by defining phi, and then we define k to be the dot product. Then this is trivially satisfied. We can show that this is just a natural conclusion that follows. However, the more interesting thing is when we start with a definition of k, and then we avoid ever using phi. We never even bother with this mapping. We just start with the definition of k. We only ever use k in our algorithms, but we prove this certain property about the function that we define, so that we can know that intuitively there is some mapping that we could have done that would have given us this k, even if we never find out what it is. So what is an example of a kernel function that can be defined directly that we would work with? It seems that the most popularly used one is what's called the Gaussian kernel or the radial basis function. Those are two different names for the same thing. And this is where we take in a point x and x prime, and then we perform the function of those 2 points like this. So so this is essentially, it looks like a Gaussian distribution, which is why it's called the Gaussian kernel. Notice that as the points x and x prime get closer and closer to each other, this becomes smaller and the entire kernel converges to A in the limit as they are equal. As the 2 points x and x prime get farther and farther apart, this becomes bigger and bigger, and so this entire term goes to 0, and the kernel then converges to 0 as these two go infinitely far apart. So this kernel is like a measure of proximity between these 2 points that we input to it. It gets bigger as they become closer, and it gets smaller and goes to 0 as they get farther and farther away. And the largest value is A, and the smallest value is 0. So it's a kernel that's between 0 and A. Okay, so we aren't going to go through proving that the result of this is a positive semidefinite matrix, and therefore Mercer's theorem holds. We're just going to state that that's the case. And so in this case, because we can prove that for any set of n points, x1 to xn, the matrix constructed from this kernel has to be positive definite, actually. It therefore follows that there is some mapping of these vectors into a higher dimensional space such that this function results from their dot product. So this higher dimensional space is actually an infinite dimensional function space for this case. So therefore, we can't write the function of x as a vector. It would be infinite dimensional, and it's actually also a function. So we simply state, without explaining or expressing what this is mathematically, that there is a function of x and t such that this kernel results by integrating the product of those two functions. So a dot product in finite space becomes an integral over a product of two functions in infinite dimensional space. So we integrate the product of these two kernel mappings over this parameter t. So we aren't going to discuss in detail what this mapping is, not because it's not interesting, it is, and it's not because we don't know what it is, we do. A good book on Gaussian processes will discuss this, but primarily because we'll see that the algorithms that we're going to develop with this kernel, this idea of using kernels, both today and in a few lectures down the road, never need this mapping. They only ever need this definition of the kernel function itself. So we only ever actually need to calculate this. We never actually need to calculate the mapping itself. Okay, so before we do this, just not to give the impression that kernels are equivalent to the radial basis function of the Gaussian kernel, there are other kernels. For example, a kernel could map an input, a vector x, like this. So you can pick out the pattern of what this mapping is. And then if we have this higher dimensional mapping, we take the dot product between 2 points, x and x prime, and we can show that the mapping then becomes 1 plus their dot product in the original space, quantity squared. So a higher dimensional mapping that looks like this, if we took its dot product, would result in this kernel function. So instead of mapping to this space and taking dot products, we could simply, if we only ever need the dot products, we could simply calculate this function. And in fact, we can show that for all values of b greater than 0, this function is a kernel as well. So for b equals 3, there's some mapping of x and x prime to a higher dimensional space, such that the dot product in that space is equal to 1 plus x transpose x prime to the b. Or for the value b equals 3.245, there's also some higher dimensional mapping. So we can construct kernels using other functions, such as this one. Also, important to know is that certain functions of kernels are still kernels, so we won't necessarily use these or discuss these in more detail, but to give some examples, if we have two kernel functions, K1 and K2, so these are two different functions that we know, both of which are kernels. For example, K1 could be the Gaussian kernel, K2 could be this kernel. And then we perform some functions of these kernels. For example, we construct a new kernel where we take the function between x and x prime to be the product of these two separate kernels on those same 2 points. That's still a kernel. Or if we add two kernels, we still have a kernel. Or if we exponentiate a kernel, that's still a kernel. So what that means is that if we take these two functions, multiply them together to get this, and then we do that for n points to construct a matrix, there is some high-dimensional mapping that would give that original function. Maybe it's not the same, it's not going to be the same as the mappings for these two, but there is still some mapping that exists.